Good afternoon. So, thank you for the introduction. My name is Jan. I work at CERN, the IT department. We embarked on our venture with OpenStack a few years ago. So I'll be telling you why. I'll start by introducing what CERN is, and what we do, how we do computing at CERN, and then the challenges we had, which of course is to collaborate, saying what kind of problems we had, and how we try to address some of those with OpenStack. How's it going?
This place.
Okay. CERN. CERN is the acronym for Conseil Européen pour la Recherche Nucléaire. So it's the European Laboratory for Particle Physics. It was founded 59 years ago. And after the Second World War, it's a place where European physicists could get together, work together, and not make war anymore. It's been working very well. It's found on the border between Switzerland and France. In fact, the data center is in Switzerland, but the offices which are next to it are in France. It's really a very international environment where we work. So our core business is fundamental physics. That's what we do. Computing is a tool for us. We do physics. We study the universe and what it's made of. We try to answer fundamental questions like, why do particles have mass? In physics there is the standard model of elementary particles with some 12 particles and 4 forces between them. How does that actually work? We know the model is incomplete, so we are testing extensions to the model. One of these extensions is Higgs theory, and that one has been tested and has been found with experimental evidence to actually work, and as you may know, earlier this week, Nobel Prize award for the theory. Another one of these fundamental questions is where is all the mass gone? The cosmologist can calculate the amount of energy and matter in the universe, and we only observe 4% what they calculate. So where's the other 96%? This is a question that we also at CERN are trying to address. We're working in fact also with astrophysicists. On the International Space Station is an experiment that is led by a team from CERN. The question about matter and antimatter, we like symmetry very much, and we do not really understand why we are here, why there's more matter than antimatter. The universe will annihilate, and we should be grateful, but still we want to understand. And then another one is the Big Bang. What did matter look like at that time? In fact, the LHC accelerator is the one experiment that's dedicated to study the conditions of the very, very, very early universe. So that's the sort of thing that we ponder over. And this is our tool, our flagship accelerator is called the LHC, the Large Hadron Collider. It's a 27-kilometer circumference ring, 2 proton beams in opposite directions. They go at the speed of light about 100 meters under the Earth, and they are set up to collide in different interaction points. That's of course where we do our experiments, the detectors that measure what happens when these particle beams collide. You can see this is a picture that was taken on some time ago, before the cloud really took over. There's just one little cloud there on the left-hand side close to the event. Now, of course, everything is covered. You can see the airport there over here with the LHCb experiment. You can see there the famous fountain of Geneva on the lake. The CERN main premises are over here. That was experiment, one of the flagships. Is next to it. CMS is not a big one. This picture is sort of taken from the top of the Jura Mountains. Here the forests are going down. I used to live here. Very nice. We're inside the Atlas cavern. The experiment was still being built here. Sometimes these big experiments, because there's on the mountain, there's much smaller than one of the experiments in the Eiffel Tower. They're referred to as the cathedrals of science, and you could actually sort of see I'm always reminded of the glass works and the big medieval people. That's a picture like this. Somewhere in here there's a physicist as well, to set the scale, here at the bottom. So it's very big. I think you should really come to CERN and see with their own eyes how big it really is. It's quite impressive.
It is very impressive.
So here you see a schematic view of the Atlas experiment. As I mentioned, there's these two beams of protons collide in the heart of the detector, and the amount of particles is very huge. The luminosity is very high. In fact, when these interactions happen, they have about 100 interactions at the same time. You can see here, this is a simulation, I believe, what would typically happen. So you see lots of tracks, as we call them. These are charged particles that come from the interaction points, and then will need to be reconstructed in those detectors. And the information that's gathered there is first filtered. So you get a lot of information, and then sent to the data center. And that's shown in this graph here. So 4 underground experiments and their typical data rates. Those are the data rates after their filtering. An experiment like Atlas produces 1 petabyte of information per second. And then the trigger farms that is reduced to a mere 2 gigabytes per second. So that basically means that we in the computer center there on the surface, on the server side, have to deal with 1 DVD worth of data every second. So what do we do with that data? So we call ourselves the tier 0 in this schematic where this web, if you like, of universities. We are the place where the data gets recorded. That's our prime objective. The experiments then run their analysis code on that data. They call it the first pass reconstruction, and the results of that we store as well. The data arrives in the 3D disk first. It's then copied over to tape for long-term storage. And another very important function that we have at the CERN data center is data distribution. There are some 11 tier 1 institutes around the world that all get a copy of that data. Not the full copy, so it's actually spread out. And this is for disaster recovery purposes. There's a lot of data, we'd rather not lose it. In these tier 1 centers, there's one in Amsterdam, for example, with Sarah. The data is then also made available, it's reprocessed, and it's typically made available to shops in the local physicists. The tier 2 zeros, so the outer layer, is over 200 universities and institutes that get their data then from those tier 1 layers. That's the way that things have been made. In addition to the real data that comes from the experiments, there's also a big simulation activity. Because the way physics works, you prepare people to experiment. And for example, the theory is we actually simulate what we think should be happening. We call this Monte Carlo data. In numbers, it looks a bit like this. We've got about 10,000 servers in our data centers. 125 petabytes. 125 petabytes of disk. We get 25 petabytes of disk per year from the experiments which you have to sort of take. So it's pretty big. As I said, computing is not really our core business, so we try to we have to minimize the total cost of ownership of the equipment, which we do by buying the cheapest of the cheapest. And that's a plus division who can attest to bargaining skills of the CERN financial people. So we buy commodity hardware and we make precious data available on that. How to do that reliably has always been a challenge. We are going to get more and more data in the coming years. At the moment, the RC is shut down. But from 2015 onwards, they want to increase the data rate by, I think, a factor of 5. We're going to have to deal with that. They're not going to increase the staff to deal with that increase in data rate. We're going to have to deal with that too. So, how do we care for all that hardware? Well, actually, we didn't do that very well. We run dedicated compute nodes, we run dedicated disk server nodes for data storage, and we run dedicated service nodes for all the, let's say, all the metadata applications that the experiments need to run. We install mainly Linux on those machines. We have our own distribution called Scientific Linux CERN Edition, which, like CentOS, is just a rebuild of Red Hat Enterprise Linux. That's pretty down cost. These applications, they traditionally all running on real hardware. We've been doing some consolidation of service nodes in the last few years on Microsoft Virtual Machine Manager platform. We've been running actually 3,500 machines on there, majority of them Linux. That worked fine. But most of the server was still on physical hardware. And this gave us all sorts of problems because the service manager team inside the data center is rather small, and physical boxes were always handed out to end users, who then all of a sudden not only have to worry about the application they're responsible for, but also for the hardware that runs on it. If a disk breaks, they only know it's because the machine is stop functioning. And managing these specific server farm was very, very bad. Virtualization helped, but not enough. Because another problem we had was that our data center used to be big. Until about 10 years ago, we'd actually get visitors from big hardware vendors and see what it looks like and how we are renting those things. That's 10 years ago. Now we should Google direct space, Microsoft. They know how to build and organize data centers. And we weren't. We sort of missed the step there. We had our own homegrown management tool sets. Quattro and CDB. CDB I mentioned there, Lemon Computing Monitor. I'm quite sure nobody here has ever heard of it, because it was ours, so you're stuck with it. So we found ourselves in trouble there. And another thing where we had big problems with this shown on this slide here, physical hardware. So from the day that the user said, I need more compute power, to the day he actually got it, our purchasing rules and regulations and tendering processes, etc., etc. On a good day, that would be 9 months. Not all. I suppose people recognize this. In the meantime, your customer is not sure what he's we're going to get much more data to deal with in the years, in the coming years. So, in fact, we were constrained on the CERN side by the amount of electrical power that can be delivered there. We could not buy more servers than all data center powers. So we started the tendering process for a new data center. We would have liked to build another one on one of the CERN sites, but that was way too expensive. So we went to the member spaces. We always have to do when we want to buy something. And the Hungarian bid came out the lowest. And we're going to have this year we have a new data center in Budapest. So we've got some 400 servers in there right now, and we are going to grow that over the coming years. As you can see on the slides, it almost doubles the capacity that we've got on the CERN side. And we're going to have to operate that with the same amount of staff. And it's, I think, 800 kilometers away. So many colleagues would like to just pop into the computer center to reset the server. They're going to find themselves difficult. So we just had to change the way we were stuck in the mountains. It was time to change strategy. So I think I've mentioned most of the things that to see on this slide here. We need to manage many more servers than we do today with the same amount of people. Our tools were getting very dusty. And we were no longer special, we realized. So we decided to adopt an open source toolchain model. Open source is something that is very close to our heart anyway. And our hope was that we would be able to leverage the deliverables from existing open source community and contribute back to them. Another thing that I haven't mentioned yet, CERN, of course, training is a very big thing. We hire a lot of young staff who spend a couple of years at CERN and then go back into the real world. To find somebody coming in and say, I know what sort of management suite, I know the Lemon monitoring, this never happens. What we'd like to see is people coming in and says, yeah, I know a bit about it. Sure, I know I can understand. Train these people up, get trained staff, they learn something, you get an important experience, and then go back onto the market, but they actually learn something interesting, done something. So, we started to prepare to move to the cloud. We desperately need to improve our operational efficiency. I've shown you the slide with the 280 days waiting for delivery. Another thing is, I mentioned to you, we were running our scientific Linux CERN distribution, which as a part of the Linux core team at CERN is the best distribution around. However, there are some customers who would really like to do something with Fedora or even with Microsoft Windows even. We need to be able to support that. These resources that idle around while they're being burned in and customers change their minds, we just need to be much more dynamic to make more efficient use of the equipment that we have on the floor. Also, a lot of the work that we're doing peaks around the time of conferences. When Atlas and CMS want to quickly go over their data just because in a month from now they need to validate the results that they would like to announce. They need peak capacity. We've always been buying for peak capacity, which basically means that we've always been we have too much equipment to worry about. We'd like to use the equipment that we have, the base load, and we'd like to be able to burst out into another cloud if there's a peak demand. So, cloud architectures became extremely interesting for us in 2011, and we started to get involved. So, what have we got today? I told you we started in about 2011. We've got a production release since this summer. It's based on the OpenStack Grizzly version. We are, as I said, basically a Red Hat derived shop, so we base ourselves on the Red Hat packages that come from the RDO community. We work very closely with them, and we find them to be excellent. We make minor modifications basically to make sure that Nova works in a CERN networking environment, but packages like Cinder, like Keystone, like Horizon, we take as they are. It's great. We allow our users to upload their own images. We recommend that they take Cloud Init into them, so that first boot of the virtual machine they can actually contextualize them to their needs. So we actually also give people base images with SLC Linux in our case, and with Windows Cloud Init, which allows people to install additional packages, create new users, and configure machines as well. And actually, we put those machines then into our public infrastructure, our public takes over. It's very good. So we've been focusing on Nova with KVM and Hyper-V as the two underlying hypervisors. We use Ceph as the image, as the backend now for our glance image store. We've actually done some original work on making sure that Active Directory is properly supported for the identity backend for Keystone. As I mentioned, we use Horizon. We're also now using Ceilometer, the metering component of OpenStack. To be able to offer Cinder volumes with the Ceph and NetApp backends is work in progress. We're testing it right now, and we hope to offer this to our customers towards the end of this year. Another very important component that we're using are the Puppet modules that live on StackForge. In fact, these were developed by Puppet Labs employee in very close cooperation with a couple of players in OpenStack, notably Cisco. And that's where he works now, I believe. And in fact, when we discovered this, we knew we were on the right track, because I told you we had our own configuration management system, and when we realized how much work it would have been to write modules for our own Quattro thing to configure OpenStack, we were extremely grateful that somebody else did. So we have a production service now. We've got two different Nova cells, one in the Wiener data center in Budapest, and another one in the CERN data center with about 700 hypervisors. And we are planning to add about 100 servers per week over the next year and a half to go up to about 10,000 to 15,000 servers. At the moment we run 1,800 virtual machines. This is the screenshot of the Horizon web interface. I've logged in as an administrator here. I've ordered the virtual machines from our different customers. They're grouped into different projects. So you see the batch project, which is the big number crunching farm, has got about 3,000 cores running in the Budapest center, about 2,000 CERN site. You also see NA61 data production, LHCb, Atlas. You see that our customers actually have got their own projects and they're booting their virtual machines in there for their purposes. And the cool thing is they can just do it, they don't have to ask us anything actually. I'm not really sure what they do. I don't have to know. I'm very happy on that. And the funny thing was that when we actually started to do this work, we realized that we weren't the only OpenStack cloud at CERN. The experiments there are actually rather autonomous beasts. Online farms, they realized they also had problems. The accelerator typically works something like 8 months per year, which means that for 4 months per year, the big compute farms in experimental areas are idle. And now, when the accelerator is being upgraded and the detectors as well, again, these farms are essentially idle. They realized that we have to do something with that capacity. And they started to look at clouds, and they actually, almost independent from us, also came up with OpenStack as the choice to use these online farms. You should check the website, they give a very nice presentation. You see there that the Atlas and CMS clouds, they're actually at the moment twice as big as the farm that we run the CERN IT in terms of number of servers. In terms of course, it's different. Apparently, our machines are a bit newer. But it's actually quite interesting because this, of course, then asks the question, so why do you have got 3 clouds? If I'm one user and I've got one application, I will submit to one cloud, no? So this is work that's in progress for us to actually be able to offer to the end user just one point of entry. So that's here on the list of things that we'll be looking at now. We are actually partnering with Rackspace to do some work on federated clouds. Because apart from the 3 clouds that I just mentioned, we also have these 11 tier 1 institutes, right? And these 200 tier 2 institutes. And rather than running the grid software, which suffers from all the problems that we've been suffering from in certain data centers, people are actually very interested in running clouds. And as long as they're EC2 compatible, the experiments will be able to set up their workload and to submit their workloads. So I think there's about 4 open source choices you can make for to run the cloud. That's OpenStack, there's OpenNebula, there's Eucalyptus, there is thank you. We see a little bit of all of them, although most people now seem to be converting copies. There are some OpenNebula clouds around that effort like in front of the European community specifically with our use cases in mind. But that seems to be trading on OpenStack. You seem to be betting on the right horse. So in our next steps, another point, I mentioned most points already, but another one that's very important for us is to get proper support for X509 certificates and for Kerberos infrastructure, which are both very important in our community. Kerberos at CERN itself and the different grid sites they use X509 certificates to identify their users. So we want to have that properly supported. I think that's going to most of that is coming in Havana. There may be a few things that we'll left to develop. And later on, we'll be looking at bare metal provisioning. Not all the use cases that we have can actually run properly on virtualized hardware. So we want to see if ironic triple O projects are develop interesting stuff for us probably a year from now. We are looking at OpenStack Lead for orchestration. So a typical case we have is that we run a cluster of web servers, and then an important event takes place, and we want to automatically scale that up as the load rises. So we're looking to OpenStack Lead to do that for us. Load balancing as a service is something that is interesting for us. Database as a service is also something that we're looking into. So there's a lot of interesting things to be done, but the core part, offering compute on the 15,000 hypervisors by the end of 2015 is something that we are doing. We are on our way very slowly to make this happen. So in conclusion, we are in production since a couple of months. We're working with the OpenStack community to make sure that we can actually scale to those numbers. As I've said on a number of occasions, being part of that community is great, and it has allowed us to be too successful here. We are not unique any longer. 100,000 virtual machines sounds like a lot. It really isn't anymore if you compare it to some of the other customers of OpenStack. And for us to be able to not just benefit from an open source project, but to also give back to it and be part of it is a very rewarding experience. So we're very grateful to all the companies out there and all the organizations out there who have helped us to make this happen, including Cisco. Thank you.
Thanks, Jan. And I saw some people in the audience thinking if they have as much VMs as you have and as much storage, and I saw some people were thinking. At the end, as big as CERN is, if you compare it with the companies here in Holland, there is a big difference, but the most important thing, what I've learned from you today is, and I hope you have the same experience in that, is you have to change the way of thinking about doing your IT and running your IT department now, and what the possibilities are in the future and what it can bring you in scalability, etc., etc. So again, thank you very much from Naturalis. Thank you for joining and giving your ideas what you have done with the audience. Same for Hans. Thank you very much. Of course, Seth, the people who are coming here to explain everything about their technology, and Ivo from Cisco, and thank you for giving also the idea that we work together on new technology, on how to bring technology easy to the market, Cisco and Fairbanks together. I would like to finish it. I look to Mark. Mark, the drinks are
Here.
Oh, they are here. Okay. So what I would like to do is thank you for being here and listening to the story. There is a drink here at the end.